Hi guys, today I will teach you how to determine the electron configuration. For example, when you Google the image of oxygen atom, you see that it had the atomic number of A. It means it had a proton and a electron, right? But why do we see this? There's two kind of like the orbit around the sun, but there's two. The first one had 2 electrons, and there's the other one outside that has 6 electrons. But in total, it has only 2 orbits. Where the outer atom of higher element we have more orbit, but why is it possible? How could we don't have that 6 electron inside and 2 electron outside instead? Why it had to be this way? Another way, when you Google the oxygen atom, you see that electron configuration. For example, you go to Wikipedia, you see electron configuration is 2s2 2b4. Why is that? Why we see this number? What does this mean? So first of all, we know that an atom is a quantum object. It means it has discrete value thing. So let's call each cell we see here. It's like n equal to 1 and n equal to 2. Let me make a few number of cells so you can see what I mean. So for example, the first orbit here can call n equal to 1, and the second orbit here can call n equal to 2. That's very obvious. So oxygen had only n equal to 1 and n equal to 2. So let's call this quantum number a cell of electrons. So this oxygen atom has 2 cells. The first cell inside near the nucleus, and the second cell outside. And the second is the subcell. The subcell determines there's only 4 subcells, but the number of n here can go on forever. But I would choose to stop that at the number 4 because it's so special. Why? So here, there is the picture I found on the internet, so to save the time. So we see here there's n equal to 1, there's one subcell that has 2 electrons. So why one subcell had only 2 electrons? Well, here we have n equal to 2, we have 2 subcells in this. Is S and D, and n equal to 3 we have 3 subset, it's SPD, and n equal to 4 we have 4 subcell, and when n equal to 5 to 6 to 7 we have also the same thing. So let's talking about 4 subcell at PDF. So we have 1 orbital for the S cell, which is closer to the nucleus of an atom, and the B cell we have 3 orbital, the D cell we have 5 orbital, and the F cell we have 7 orbital. What do it mean? So 1 orbital can occupy the maximum number of electrons is 2. So 3 orbital occupy the maximum number of electrons is 6, and the 5 orbital maximum is 10, and 7 orbital maximum is 14. So why do it have occupy only 2 electrons? So it had to do with the quantum mechanical effect of the Pauli exclusion principle. So it says that 2 particles can only occupy the same state at the same time if they have different in something. Some quantity must be different, otherwise they cannot. Then that quantity is called spin. So a particle can only have 2 spin states, that is 1 spin up or 2 spin down. So if an electron occupies spin up, that other electron must have spin down. So you cannot add the other 3 electron because it will have the spin up or down, which is the same with the first or second electron. So you can only occupy 1 electron. So according to the Pauli exclusion principle, this is the maximum possible electron you can get for each orbital. So for the S cell it's 2 electrons, for the B cell it's 6 electrons, and for the E cell it's 10 electrons, and for F cell it's 14 electrons. So that's very easy to understand, right? So let's say that we have 2 oxygen atoms. So here is the rule that I have to show you. It's called, now this diagonal rule is called the outpower principle, but I don't have the explanation for it for now. So let's just assume how do we write, for example, an atom. So first of all, we just said in that there is 1s2 and then 2s2. We keep going here, then we go here, and we continue to B6, and we continue to 3s2, and we continue to 3b6, and we continue for 4s2. So the energy level, the energy just go up. From the S it had lowest energy, 4s had highest energy. But what do this mean? So the number here, the number on the power is actually the number of electrons. So if you add all of this number is equal to the number of your atom, you get an element that decide what you want, because an atom had equal number of proton and electron in order to be neutral. Say you have the oxygen atom again, which the number of atomic number is A. So begin with the rule here. You just need to write the number. So 1s2 first, then 2s2. That is 4 electrons right now. And we go on to B6, but we see that the 6 here plus 2 is actually 10 electrons. So we have to reduce the last number for the last subset of electron to make it equal. So you know that oxygen had 8 electron to be neutral, so we have to add 4 here. So this is the definition of the atomic configuration, the electron configuration of the oxygen atom. So we can see clearly here that we see, let me clarify this. We have n equal to 1. We have n equal to 1 here. We just say that 1s2. So we just do it here. And this is where we get n equal to 1. And 2s2 to b6. Actually here. The entire here is 2s2 to b6. But remember, we only have 8 electrons, so this last number is reduced a little bit. So we have this n equal to 1, and this is n equal to 2. Right, n equal to 1 because here we have 1s2, and when come here and here we have n equal to 2. And let's look at this oxygen atom again. Now 1s2 has 2 electrons. This is where n equal to 1, which is the inside orbit I talked before. So number of electrons is 1 and 2. So n equal to 2, the number of electrons is 4 plus 2, which is 6, which is exactly what we got. 1, 2, 4, 3, 6. So that's pretty cool. So we got the number of oxygen atoms. So go back to Wikipedia. Wikipedia say that oxygen atom had electron configuration 2s2 2b4. What does this mean? Well, technically it's this number here. The last two numbers is always used. So we use this standard number, two last number, for classify an element. So let me do with iron, for example. Iron had 26 electrons, so I need to go a little bit. We had the table here. We just bring the table here to calculate. Let's say that 1s2, 2s2, 2b6, 3s2, 3b6. Let's count the number. Okay, we go to 3b6 here. And we realize that after that we had to go to 4s2. Alright, so we have 2 near electron now, and we go to 3d10, but remember we have 6 electron plus 2 near 26, so we only have 6 here. So this is the orbital configuration of electron when right in the contract form. So let's try to Google iron. So 3d6 4s2. Oh yeah, so we have 3d6 and 4s2, which is exactly what's got here. So that is technically the order doesn't matter though, so we see that exactly what we got here. Now let's try to write the atom of iron. Now we have the nucleus, the center. we have the electron. So let's try to determine we have here is the n equal to 1, and here is n equal to 2, and here's the n equal to 3, and here is the so here belong to here is n equal to 3. So here's the only thing that had n equal to 4. Let me write, it's left a bit confusing. Sorry, so I'm going back here. So you can see there's a bit confusion because we determined the cell which is depend entirely on this sequence, because due to the 3D10 which is variation in this, and we have the right is after the 4s right here, so the 4s2, then we have 3D. So we got n equal to 3 here, but it doesn't matter. We see n equal 1 had 2 electron, n equal to 2 must have a electron because 6 plus 2, but n equal to 3 kind of tricky. We have to add 2 plus 6 equal to a, then we add 6 right here, so this is we have 14 electron. So n equal to 4 is easy, we have only 2 electron. So this is exactly what I found on Google, 2a142. So the inside had 2 electrons, the second side had a electron, the second orbit, the third orbit had 14 electrons, and the final orbit had only 2 electrons. So that's how you determine that.